Welcome, everyone, to the invited talk by Professor Philippe BLANC with title Solar Resource Assessment and Forecasting Using Earth Observation and Data Sciences. We will start with a short welcome note and we will then proceed to the talk. The talk will be recorded, so please turn off your microphones. Also, Professor BLANC plans to have this talk for about 40 minutes, leaving room for discussions during and after the talk, so we can have a living and unique session. And at this point, I would like to invite Dr. Konstantinos Frankos, leader of the Energy Cluster of ERATOSTHENES Centre of Excellence, for the welcome note.
Hello, maybe should I stop the sharing, or is it okay like this?
No, no, it's fine. There is no problem.
Sorry.
I will be very short, just to introduce you, and then we can proceed on your presentation.
Thanks.
Hello from my side. Also, we would like to thank Philippe BLANC. It's the head of the Department of Energy and Processes of Mines Paris PSL and the deputy head of the Center of Observation Impacts Energy. He's working on the modeling of solar radiation and its assessment and forecasting from in-situ measurements, numerical weather prediction models, and or satellite images, mostly from Copernicus. His background is related to signal and image processing, data sciences, and applied mathematics. He was associate editor for the ICES Solar Energy Journal that it's through Elsevier for 5 years, and he's currently the leader of the subtask of the second subtask group and heads data and backup projects of the task 16 solar resources for high penetration and large scale application for the PVPS program of the International Energy Agency. Professor BLANC, the floor is yours, and thank you again.
Thank you very much for this introduction. Thank you, Georgia, for all the organization and the very kind exchange we have, very gentle. And by the way, we met together last year, no, not last year, at the beginning of this year. And it was nice to meet you then. So thank you very much for this. And thank you for giving me the opportunity to have this talk about the Earth observation and the link we can have between Earth observation, solar resource assessment and forecasting using, let's say, the cutting edge as far as we can about data sciences. Okay, so PSL, as introduced previously, is a integrated university, rather recent, 2010, sorry. And within this PSL, we are a school of engineering. There are 3 schools of engineering in PSL. One of them is Mines Paris. And Mines Paris is an old school. It's not as old as NOAA, but let's say 1783. So it's a rather small school. We are less than 1,500 students, including engineers, masters, PhD, and executive training. We are 230 teachers. And we are, in fact, not only a school of engineers, but we have also research centers organized around 5 departments: materials, geosciences, mathematics, social sciences, and energy and processes. I'm the head of these departments, and within these departments, we are 3 centers, 1 in Paris, 2 in Sophia Antipolis. So Sophia Antipolis is not in Paris, but in the southeast of France, close to Nice. I'm a researcher in the Center of Observation Impact and Energy. We are about 25, including the PhD students and the postdoc. And we are doing observation of resource to environmental impacts for renewable energy. So we have 2 groups, one dedicated to the Earth observation and the assessments of the renewable source of energy, and more specifically on solar. And we have another group dealing with life cycle analysis for environmental impacts of different energy pathways, looking at renewable energy compared to other sources of energy, and to compare and to make some public decision on the energy transition. So I can just give you a flavor. It's not the topic of this talk, of course, but we are doing some assessments for individual energy system, go to sectorial level. So we are interested in, for example, the pathway of photovoltaics compared to others. Then, of course, when we want to go to energy transition and public decision, we have to incorporate this type of analysis in scenarios to make some comparisons. And then we can we are extending this environmental assessment with sustainability assessments, including financial part, environmental part, and societal parts. So this is what we are doing in that matter. But I will focus on the group about renewable energy assessment with Earth observation. So dealing with Earth observation and solar resource, it has started, let's say, in the 80s with the development of heliosat methods. So heliosat method is dedicated to estimate surface solar irradiance from the radiance coming from the Earth and measured by geostationary satellites. So we have started with Meteosat first generation, and so heliosat 1 is about in the 80s. We have developed the heliosat 2 in 2004. It's more than 1,000 scientific citations and many applications, and also modification from this version. For example, Solar Anywhere, Solar GIS, SODA are based on heliosat 2 method or derived from heliosat 2 methods. So it's a cloud indexed method for people who are interested in more particularly. In 2013, we have developed heliosat 4 method. So it's a physical approach. It's not based on clone index, but we try to describe the atmosphere effect on the solar radiation. It's close to the NSRDB database from NREL, for example. And so we will see that this heliosat 4 method is on operational level, and we will discuss this afterwards. And in 2021, we have developed a heliosat 5 method within a PhD, and you will see that it's not only applicable to Meteosat Meteosat satellite, but other non-geostationary satellite as well. We are doing research. What the particularity of our research center is to be able to work for R&D projects with institutional bodies such as European Commission, the French National Energy Agency, etc., but also with partnership of industry, Total Energy, EDF, ENGIE, Somfy, Google, and also small and medium enterprise on PV developments. As said during the introduction, we are working with the International Energy Agency within the PVPS program, and more specifically in the STAS 16. So I engage you to register in this, so you can be part of this task, because it's dedicated to solar resource for large-scale application of photovoltaics, and it is there where we are discussing in situ measurements, satellite derived, and all the products we can have, very close to the presentation I will do. Okay, so if you're interested, we have here the line of the publication of the center. So what I will present now is about what kind of observability related to surface solar irradiance we can derive from Earth observation. So here mainly I will talk about satellite data and in situ sensors, and we discuss all the different types of in situ sensors. Then we will discuss about downscaling satellites-based surface solar irradiance retrieval with digital surface model for PV development at urban scale, very specifically because we think that it can be one of the subjects we can work with you within Atari, and also about satellite-based intraday solar forecasting to have some ideas about this. So what are the sources of Earth observation we can think about? So if you see this graph, in x-axis you have the space scale, in y-axis you have the time scale. It's a schematic, of course. At the larger scale, in time and in space, you have the numerical weather and reanalysis and chemical transport models. It can be this. On the opposite side, at the low very high, lower scale, space and time. You have the in situ measurements with new emerging in situ measurements, notably the fisheye cameras, and we will discuss about this. And between this point and this point, there is a gap of time and space resolution that can be filled by satellite data. And so the reason why we were, since the 80s, involved in the development of algorithm dedicated to the SSI retrieval from satellites. So Heliosat 2, Heliosat 4, Heliosat 5, and we will see that we are still on the research about this, this family of algorithm. Okay, so when it comes to the observability, then you can talk about the observability of the clear sky variability. What about the turbidity of the atmosphere? If you do not have any clouds, okay, so you still have some variability, because in Europe and US, you may have this, let's say, bias, thinking about variability of solar radiation uniquely due to the sun position and the clouds. But now you have also the variability induced by the turbidity, and so the turbidity can be, let's say, variable because of aerosol and water vapor. So to do that, we have developed within the Heliosat 4 method, a method based on LibRatran. It's a radiative transfer model that we have parameterized and simplified to go as a fast computation with lookup table. And so we have used the aerosol water vapor coming from CAMS, which is the Copernicus Atmosphere Monitoring Service. So they are providing us with reanalysis product and forecast products on water vapor and aerosol optical depths at different wavelengths. It comes with, let's say, approximately 40 kilometers spatial resolution with a worldwide coverage, and temporal resolution within hourly to 3 hours. And we need also, for the diffuse components, the amount of energy coming from the grounds and coming back from the sky albedo. So we need this ground albedo, and for that we are using a MODIS database that we have derived as a climatology of monthly basis of BRDF parameters at 6 kilometers, but at monthly basis. So this is an example of variability you can have on global horizontal irradiance at a daily basis. So each frame is 1 day, so 1 day to another one. You can have not due to the clouds, but due to the aerosol optical depths, the dust, for example, for the North Africa. So it's very important to take this into account if you want to capture all the sources, important sources of variability, notably in Africa. And of course, you can have these daily values, but you can have intraday variability induced by atmosphere turbidity. And this is an example of the dust event occurred in 2021 in February. And you can see the clouds, the dust events going from the southwest to the northeast. And you can see the effect of this cloud event, dust events with the McClear, accounting for the aerosol optical depths estimated by the CAMS atmosphere aerosol data. So this can be provided at, let's say, 1 minute basis, worldwide coverage for free. And it provides the global horizontal irradiance, the diffuse components horizontal, and the direct normal irradiance. When you want to observe the clouds, of course, Meteosat or geostationary satellite is a very nice way of observing in a persistent way with a high resolution in space in time high. It's relative. So, for example, Meteosat second generation, you have 3 kilometers, all the full disk, 1/3 of the Earth, and you have this since 2024 and up to now. And we will have soon, and we have just, let's say, a few days ago, the images coming from the FCI, the Meteosat third generation, with a gap in terms of spatial, temporal, and spectral resolution. So we have to be prepared, and we will discuss this afterwards, with these very nice images coming from Meteosat's third generation. So from this, we can derive, applying the Heliosat 2 method, some estimations since 2020 2004, sorry. And it's already commercialized by soda-pro.com, now with Vaisala. So you can buy this data. It's not for free, but you have from Elosat 4 method, thanks to the European Commission, you have another method applied to the same satellites, and you get the same temporal score and spatial coverage, 15 minutes resolution, 4 kilometer resolution in space, coming from CAMS, so the service CAMS radiation, and this is for free. And in 2021, we have developed the Elosat 5 methods. It has been a PhD from Benoît Tournadre. So it's a nice paper. You can get this paper for free and get the information. And the idea of this method is a cloud-based method, but applicable not only to Meteosat, but other satellites, geostationary satellites, to go towards global database. And since you are in the geostationary satellites domain, then you need more than one, of course, because with only one, you get 1/3 of the planet. So if you want to have the global coverage, you need more satellites, and maybe Imawari and all the satellites from US Gus satellite. So this has been dedicated to be applicable, easily applicable to this new satellite and also all satellites. So it's very versatile. And it's so versatile that it has been applied to a satellite that you may not know because not well known. It's a very nice satellite, by the way. So it's a satellite in the L1 points of Lagrange. So here is the Earth, here is the Sun. And you have a specific point that is stable in gravity. And you can put satellites. So here, Discover. And within this satellite Discover, you have EPIC sensor, which is RGB and other channel of interest for the atmosphere. And so it's away from the Earth about 1.5 million kilometers, but it has the specificity to have always the sun in your back. So when you look at the Earth with the satellites, it's not like the geostationary satellite where you can see the night and the day because you are rotating with the Earth. Here you are rotating with the sun, let's say, and so you have the sun always in your back, and so you see only the part of the globe that is lighted by the sun. So by the way, with this satellite, you can have a global coverage of surface solar irradiance retrieval with only one satellite, but it's far away. It's 1.5 million kilometers. So there is two problems: the resolution. So here is the 20 kilometer resolution, which is nice considering the distance. And we have another problem: there is a problem of antenna. There are not enough antenna to get the data for Discover. And so if you are interested, indeed, but it could be of interest for you to get the data from Discover because it's a nice source of data for surface solar irradiance. If you want to go to higher resolution observability of cloud variability, then we think that fisheye camera is very of interest in addition to parametric sensors. So parametric sensor, the pyranometer measuring the global horizontal irradiance, the diffuse horizontal irradiance, and the pyranometer for the direct normal irradiance. And you have a very specific instrument that we like very much, and we will discuss this afterwards, the SPN1 with no moving part measuring the direct and diffuse. And thanks to the fisheye camera, you can have hemispherical sky images as a video frames. So you can see here it's a day. You can see the cloud moving. You can see the sun position. You can see the direct components here in the circumsolar region. And when you have a cloud in front of the circumsolar region, it means that you have a cloud shadow on your place. So it paves the way of many applications from surface solar irradiance measurements or quality assurance for the in-situ measurement, because you know the state of the sky when you have measurements. But also it's very useful for forecasting. And if you look at the work from Andreas Katsanditis, you can see a lot of applications you may think about with the fisheye camera, notably aerosol optical depth measurement with fisheye cameras, and among others. You can also, there are many papers, and I can make a conference only on fisheye cameras if you are interested in. It's almost a passion for me. Okay, so we are working on parametric sensors. So we are very interested in collecting the data because it's a very important sources of information, the best information you may have in a local place if it's properly maintained. And since we are developing surface solar irradiance retrieval with satellite, we need calibration, we need estimation of the quality of what we are doing. And you will see that it's even more important if you go to data science and machine learning approach that we can discuss. Then you need in situ measurement, both to learn and also to test. So in that sense, we have developed different ways based on the FAIR principle. I will discuss this afterwards, open approach, to get the data from different network of in situ measurements, to ease the access, to ease the readability, to ease the finding of this data. So we have developed a thread server and a web viewer. And Georgia, you can get the presentation and all the links are active and you can click and see the web viewer and the thread server if you are interested in. I think it will be part of Atari as well to discuss about this way of doing if you are interested. So the FAIR is very important because we are looking for data to be reusable for the science, accessible, interoperable, so you don't need to change one network to another one, the way you are retrieving the data, decode the data, and try to be, and findable also. And so from this that we have developed, so we have developed a specific open source library in Python, libinsitu, that is the process of getting the data and do the quality check of the data. So everything is explained in this part. I don't have time to go into much detail, but you can see example in a Jupyter notebook to get the data, to quality check the data, etc., etc. So, and it's part of the job we are doing in Solar Winter School, by the way. As an example, also, we are interested in, so this is the observability. So the satellite, the in situ measurement, the fisheye cameras. Okay, this is our source of observability of surface solar irradiance. Then I will explain you how to use it, for example, in different situations. Here we are interested in having a solar assessment and forecasting as a service. We will explain what does it mean at urban scale. So we want to downscale the data from satellite to go from, let's say, few kilometers to few meter resolution. Of course, not every sources of variability, because the cloud is not only observable from satellite at 3 kilometers every 15 minutes. But here we have, in the urban scale, we have these sources of variability induced by the buildings and the vegetations, the slope of the PV module that you may install in your roof. So having this, to take this into account, we have developed a service in the cloud as an exercise to downscale, to downstream the service from CAMS, for example. So going from the clear sky and the CAMS radiation with the clouds, downscaling with a web processing service. So you select a region and near real time, you get high resolution, let's say less than 1 meter, less than 1 minute resolution, integrating the effect of shadows from the ground. And for that, we need digital elevation model, which is widely, for example, SRTM is almost everywhere. But we need DSM, digital surface model. It's a digital model of the city. And we need this at 20 centimeters. And in many places, you can have access to this data. And we thought about this methodology to be agnostic to the source of data. So it can be LIDAR data, it can be Pleiad, for example, or I don't know. So there are some satellite 30 centimeter resolution public satellite. So you can get also data from this type of sources. And then downscale. And thanks to this downscaling, you can have different use cases to downscale of this downscale solar radiation resource. For example, here, It's the premise of the School of in Paris. And you can see, I don't know if it's is it working, Georgia? You can see, so it's the computation is. So the computation is about, let's say, 5 or 10 minutes computation. It's 50 meter resolution, 50 centimeter resolution every 5 minutes. And you can see the quality of the DSM inducing these shadow effects. And of course, if I'm interested in putting a PV panel on this roof, then I can have the shape, the time series of solar radiation and the time series of PV output, taking the slope and taking the shadow into account at urban scale, data coming from long-term series since 2004 from CAMS, for example. And this type of application is very interesting to do PV self-consumption, to cross energy demand and PV production, to do the self-consumption. It is important also to use for PV integration in the grid. So at not individual sites, but for a block of city regarding to the grid, the DSO, the DSO and the grid management for the point of the grid electricity, how much the energy will get from these PV modules if it is installed in the city. And it can have also some nice application in solar forecasting. If you are interested in solar forecasting, then the shadow at urban scale can be very important to take this into account. So, for example, this is an example of Marseille. So it's a big city. I don't know if I have time to go. Yes, I can have a few minutes to go. So to see the fact that we can go with this type of tools, very specific to a house, but also to have a large-scale application of this type of approach. So this is an example of application of these services for the city of Marseille. So it's a big city, 240 square kilometers. And if we look at only the yield, yearly electric consumption is 3,500 gigawatt hour. And despite the fact that it's a sunny part of France, only 0.4% of this electricity consumption is coming from PV. So there is a large margin of progress for the PV. And if we look at the footprints of the building, then just roughly you can say that, okay, the theoretical PV capacity is 5 gigawatt peak, producing more than twice the amount of electricity that Marseille is consuming. Okay, just looking at the footprints, and so it's a very rough estimation because you have shadow and you have tilted and etc. So using this SAF approach, you can, with LiDAR data, so in France, we are lucky, we have this 10 centimeter resolution LiDAR data from which we can derive this digital surface model. And so we can filter out places where the slope is too high or it's not plain enough to put PV on the roof. So we are looking for local planarity. And then having filtered out of these points, you get only 12.3 square kilometer available for PV, potentially, not looking at the shadow, but just looking at the shape of the building. And of course, this value is not, we should add the parking areas because there is a lot of parking areas that we can cover with PV. And since we have this solar downscaling up capacity, we can derive some solar cadastre. What is a solar cadastre? Is a map of yearly values of global tilted irradiance that you can derive in PV output. But you have this spatial resolution of less than 1 meter, but you have lost, of course, the time resolution because otherwise, if you want to keep 15 minutes for the whole Marseille, it's too much data. Okay, so the idea is to be able to have a map, and then when you are interested in a certain points, then you can have locally both the spatial resolution and the temporal resolution. So this is an example of solar cadastre derived from using the SAF method. And then thanks to that, you can have a better analysis of the solar potential. So I talk about the 5 gigawatt peak theoretically, but when you look at closer, then you see that it depends on the quality of surface solar irradiance you have on your on your square meter. Okay, so depending on the cost of the PV, maybe you don't want to install when you have only 1,100 kilowatt hour per square meter, because it will be too expensive to put panel on such shadowed area. So for example, if you opt to this threshold, which is depending on the cost of the PV module, then you have this, let's say, more fine analysis of the solar potential in Marseille, which is approximately 1.5 gigawatt peak, corresponding to let's say, 2/3 of the electric consumption of Marseille, which is not negligible, but not twice the value of the electric consumption. Okay, so have a thinner solar potential thanks to CAMS and downscaling with DSM from LiDAR data. And of course, it's not a big deal in terms of computation. Okay, consider the city of Marseille. It was only 40 hours of computation. And of course, if you are interested in very specific places, just like this one, so I have selected randomly a roof in Marseille. And so I'm interested in having a time series taking into account the shadow around. Then I can get in seconds this time series from years of data since 2004. And so derive some, let's say, this is an example for the month of May 2023. This is the box plot, 50 minutes per 50 minutes of the solar radiation, or the PV output, sorry, PV output you may have because of the weather, the clouds, and the shadow. And of course, in this position here, let's say in May, there is not so much shadow. But if you consider in December, then the configuration of the building around is quite different, has quite different effect on the shadow, and you can see the loss of PV output when considering the shadow in December. And of course, you can have the time series and better understanding where does it come from, the shadow. So it's coming from this building in the top right here. So at the southwest, and you can see the shadow of this building cutting the production of the PV during December. This is an example, of course. Okay, so we are also interested in, so this is about the surface solar assessment and forecasting as a service at urban scale. And now I switch to another application. It's about what we are doing in solar forecasting, and notably solar forecasting using satellite data. So since satellite data, we are not dealing with, in that occasion, numerical weather prediction. So the idea is to do the forecast only intraday. Okay, so few hours ahead, maybe 1 or 2 hours ahead using satellites. So the idea is that we have a sequences of images from Meteosat, from which we are deriving the surface solar irradiance every 15 minutes. So since we have 2 images from separated by 15 minutes, we can derive the speed of the cloud and make some computation to assess the amount of energy we will get in, let's say, 10 minutes, in 20 minutes, or in 1 hour. And since we are doing, so it's a paper that we have made, it's open source, so you can get, there is a link here. So you get not only a deterministic value of the forecast, but you have an access to the probabilistic. So meaning that here is the time frame in red, here is the time ahead, sorry. And so you can see that sometimes you have spread, and this spread is because you have some multiple possibilities, multiple errors in the estimation. So it means that you have a sort of distribution of uncertainty or variability induced by inherent to the solar forecasting. So then what we think is that deterministic forecast is interesting, but the active research is more on the side of probabilistic forecasting. And this is a way, an example of doing this satellite-based probabilistic forecast in intraday. Of course, it's still active because it's very complex to do the forecast with because we have a lack of resolution from satellite. And we mainly have this assumption of advection of clouds. So we see the cloud moving, and we expect that the clouds still have the same wind speed, transporting the cloud in a very simple manner. So of course, it's not always the case. You know that it's way more complex than that. So we have situations for which we are failing in the solar forecasting. So this is a work done by Yves-Marie, a colleague of mine in my center, and a colleague in Paris, in École Polytechnique, Laboratoire Météorologie Dynamique, LMD. So they try to get some cases where this CMV, Cloud Motion Vector satellite-based forecast is failing. So, and this should be the basis of the next generation of forecasts, and to test on situation where the CMV is failing. We can also use fisheye camera to do the forecast, and this is an example that we have. It's now a rather old example of forecast based on fisheye camera. So we had this chance in a European project named DNI Cast. It was with DLR in the south of Spain with CIEMAT and other, of course, other colleagues from other institutions. So we were in these work packages, we were interested in forecasting the DNI and in a very specific way using fisheye cameras, and not a one value, but a map. Try to forecast the map of shadow, let's say. So for that, we had a very nice playground in Almeria with 4 fisheye camera and I don't remember, but more than 10 pyranometer. And the distance between 2 cameras was approximately 500 or 600 meters. So this is an example of the camera looking at the same situation, cloudy situation at the same time, but from not from the same point of view. So thanks to this parallax effect, we can assess the cloud base height of the clouds. And thanks to the video, we can assess the wind speed at this altitude. And thanks to that, we can have videos of altitude of the cloud coded with the color estimation and the wind speed estimated and represented with these arrows here. And thanks to this type of analysis, we can derive some TNI intraday forecasting spatially resolved. We were interested in also in a PhD ended in 2018. We were interested in what if we have only one fisheye camera, but having both fisheye camera from the bottom and satellite from the top. Can we derive something of interest using this cross information between the top Meteosat and between the bottom a fisheye camera? So we decided to go towards this direction and say that, okay, it's not possible to do parallax stereoscopic analysis because the gap in space and in time resolution was too high. It's difficult to locate a cloud from the fisheye camera and to locate it in Meteosat images. The gap is too high. So the idea is to make the pixel carving. So say that, well, okay, I have the fisheye camera, so I'm detecting the clouds on my images. It means that the cloud should be here in this blue volume. From the satellite, I know that I see this cloud, so this cloud should be there. And when we do the intersection of the two sources of information, then you have a restricted area where the cloud should be. We don't know where exactly, but we have this volume. And from this volume, you can have the shadow cast on this volume and see where will be the shadow. So this is an example of situation we can derive the 3D clouds, sort of 3D clouds, from the one fisheye camera and the satellite. I don't have time to go much in detail in that example, but this is an example of real application of gold mine off the grid activity using diesel and photovoltaic system. And if you want to decrease the amount of fuel you are consuming, then you have to switch off the diesel generator, and to switch on in case of cloud passing, decreasing the amount of PV output, it takes 15 minutes. So you need a forecast at 15 minutes, a very, very fine forecast for 15 minutes for this operational use of PV and the diesel generator. And this example is operational with no, for the moment, and they will add, with no storage. So it's a difficult job. So for that, we use satellite and a large number of fisheye cameras to make a sort of solar fence around the PV module and see the cloud coming to make the generator switch on proper time using fisheye camera. So this is an example of operational activity made by Solaris and SPI. So I don't know, okay, I have too much to say in fact, but what I want to say in that slide is that we can do many algorithms for the forecast, but the problem is the metrics, how to know if we are doing a good forecast or not. And there is a gap between the value for the users of this forecast and mathematical assessments based, for example, of root mean square error of the forecast. The gap is very important to understand because you may have different type of forecasts. This is an example. The red curves are for different forecasts, and they have the same RMSE, same root mean square error, but definitively not the same value. One is lacking from time variability. One is noisy. One is always in late because it's persistent. And they are exactly the same RMSE. So this is a very important discussion we have in the academy. Still, this how to better understand the quality of the forecast and the value for the forecast for the users. And this is active discussion we have within PVPS, for example, task 16, about the understanding of metrics and towards the value of the forecast beyond the metrics. Okay, so a few words about what is coming for us. I presented these sources of information, but in fact, we have way more information that coming now from Copernicus, from other satellites, from citizen science, a bunch of data we can use, but they are very complex because different nature, heterogeneous, multidimensional. So the reason why we are very interested in using data science, advanced data science, to take all the information into account to try to increase the spatial and temporal resolution and other resolution, spectral, and etc., to have a better understanding of surface solar irradiance, making based on all the sources we may have from Earth observation, and you see the diversity of this information you can have. So it's a reason why we have developed a sponsorship share. So the name is CIDOSOL, Data Sciences for Solar Energy in English. And we have some partners that help us to do this open research about this link between data science, advanced data science, and solar energy. So the idea is to, I'm accelerating, to do research, to do transfer, and to do training. And you will see example of research and example of training. So we want for the training, for example, we are a school of engineers, and we try to be attractive for our students because they don't know that solar energy and solar radiation can be very, very interesting in a mathematical and physical point of view, and also not only for the climate change. So to attract engineers to our domain and to be sexy enough, let's say, for that. And also to attract PhD students as well, of course. For the training, so you know, and Georgia attended to the previous version. So under the umbrella of CIDOSOL, we are proposing for free for the students a solar winter school. So the next will be the 10th of March, 10 to 14. And so you can register at contact@cidosol.fr. You can do it now. And you can see in the website as well some information. And so the idea is to have lectures about solar radiation modeling and forecasting, practical workshop on parametric measurement and solar forecasting, and also, and Georgia knows that, networking session with conviviality as well to foster collaboration and scientific stays for the students as well. And this is my last slide, a little bit in late, and sorry for that. So we have within the umbrella of CEDOSOL, we have 3 ongoing PhD students. One, Vadim, is looking for deep heliosat, so a new version of heliosat, the retrieval of SSI from satellite, not using physical model only, but also using data science approach, machine learning approach, using learning from data coming from in situ measurements. So it's a reason why we should have a high quality data, very dense network to do the learning and to do the tests of generalization. And what we learn is that it's very sensitive to the quality of the in situ measurement we are using, of course. And the generalization is not going very well, even if RMSE metrics are very good, much better than heliosat-4 method, for example. When we look at the details, we can see some very strange behavior of this machine learning-based approach. And we observe that there is a need of putting some physics constraints to have both high quality in terms of RMSE, etc., but also a normal behavior of the estimation. So I don't want to go into more detail, but it's very challenging to use a machine learning only approach to derive SSE from satellite. But it's interesting, and it's not obvious to see like this. But once you have a machine learning based approach for SSE retrieval, it's way easier to install in operational ways than a physical model with a library and many things that many bugs. Here it's a machine learning approach. You deploy your network and then it works. So it's easy to for the operational. We have someone that Max is looking for the fisheye cameras and make some simulation of fisheye cameras to ease the sizing of network of fisheye camera, because it's always the problem. What is the distance? What are the spatial resolution and temporal resolution? And what are the performance of the retrieval from these fisheye cameras? So the idea is to have a fully simulation process to be able to apply some algorithm and test the quality of the algorithm in the simulation domain. And we have someone interested, José, interested in downscaling the surface solar gradient from satellites, not only with shadow effect, just like I've presented, but what we want is to downscale in a statistical way for the cloud variability. So it's very challenging, and we are investigating different techniques from statistic to machine learning to do this downscaling at high resolution, both in space and in time. And it's very important, for example, for the PV variability, depending on the size of the PV farm, and to know better about this variability for the sizing of the storage, for example. And we have a coming PhD student coming for fish SPN1, sorry. It's the use of the SPN1 sensor, which is very specific, measuring the direct and diffuse with no moving parts, very smart instrument, but biased. And the quality is not very good for now. And the idea is to develop the fisheye camera, low cost, open, to be installed, to have a proxy of the sky radiance with this camera, and then correct the SPN1 to provide with a very nice diffuse and global with, for example, the SPN1 and the fisheye camera. That's it for me. I hope that it was not too fast. I wanted to have an overview of what we are doing, and now I'm ready to answer any of your questions.
Do we have any questions from the audience?
If nobody else, I can ask a question. Have a question. First of all, thank you for this interesting presentation. I think it covered a lot of interesting things from different scales and the whole structure, how the forecast can be used in actual city urban planning or in the grid operation. What I would like to ask you is, we also have some cameras. We also have one camera here at ERATOSTHENES. It's an AC16.
Mm-hmm.
It's from MECO.
Mm-hmm.
The algorithms can be the same with the Mobotics. I know that it's not commercial. It's not to say it's not scientifically graded camera.
No.
It's surveillance cameras. So the same rules can apply also to cameras like ASI. That okay, they come with their own software, but I think that image processing can be more advanced than what they have.
Yes, it's the reason why Mobotics is very nice because it's a security camera, and it's very nice because we have a strong experience now, thanks to the DLR, for example, in Almeria. It works perfectly well in a very harsh condition, semi-desertic condition. And by the way, one of my students had an internship in Svalbard, 75-degree latitude, and the camera is also working in that situation as well. Mm-hmm. And it has passed 6 months with minus 40 degree, with wind and ice, and it works very nice. So it's recognized as being very robust for the harsh condition, but there is a but. You don't have the end of the parametrization of the camera, and it's you can't change the resolution. It's difficult to change the time acquisition. You have mandatory compression that degrade the quality of the image. For the camera from ECO, I don't know because I didn't handle this type of camera. But what we have in mind is to provide the scientific community with open camera, with open plan, low cost. Let's say we are targeting 200 euros, for which you have all the data, all the parameters at your hand. So you can use one of the challenges, to have a nice scale of radiance measured by the camera from the horizon to the circumsolar region. And it's difficult to have, in fact, because there is a problem of time acquisition and saturation. And so this type of camera we are targeting, and we have some already very promising results with HDR acquisition, high dynamic range. Mm-hmm. So it's in fact, it provides free acquisition with 3 different time of acquisition in Rafale mode. And then you can compose the image with the horizon coming from the largest time acquisition, the medium sky coming from the medium time acquisition, and the short time acquisition is for the circumsolar region. And then you can play with the raw data, no calibration, no compression. And the idea also is to have on board a Raspberry Pi computer to do the main the main processing. For example, the geometric calibration, the cloud detection. Of course, you can do yours, but you can use the one that we will provide for free. So this idea is that we like very much the fisheye camera. You understood that, and we want the scientific community to adopt the fisheye camera and to make some measurement in many places, as many places as possible.
Mm-hmm. Maybe in the framework of Atari could be a nice idea to see also
exactly
how the images from here and the configurations that we could have, and maybe a small scale campaign to compare.
Exactly, and it's not I'm sure that in Cyprus it's not the same source of variability. We are used to have variability of clouds, and in Cyprus it's not the same. So it's very interesting to see the observability of aerosol, for example.
Yeah, we have a lot of dust here.
Yes. So, and dust make a coloration of the sky.
Yeah.
And this can be monitored by the Fisher camera. There are some papers from studios.
Thank you.
You're welcome. Thank you for your interest.
There is also a comment from the audience. Rodrigo
Yes.
asks if you can discuss a bit about the integration of physics in machine learning frameworks.
Yes.
Since these are traditional statistics only.
Yes, it's exactly the core of the PhD of Vadim, because we discovered that only using statistical learning, then there is for sure your set of sessions you have for the learning will not get all the situation that you can get in other places. So we have some example, where albedo or surrounding albedo can have, of course, a very important aspect for the surface solar irradiance retrieval, because it's the part of the radiance you get. So if you don't know the albedo, then there is a problem. And when we are doing the statistical learning only using no information about the albedo, then when we change in a place where the albedo is radically different, then we have a large bias. So it's the reason why it has, for example, it's easy to understand that using albedo needs to describe why albedo is important. So inject more physical knowledge on the statistical learning. This is an example, but there are dozens of schemas we can think about to inject physical constraints, for example, distinguishing the diffuse and direct, and not doing the global horizontal irradiance in one time. You know that it's two processes, one coming from the sun, one coming from the sky, and then it's not exactly the same learning. So it's good to separate the two and then make the estimation at the end of the sun. So these are different examples we can think about. And Vadim is looking at other schemas to inject physically informed approach for the deep learning approach.
Yeah, thank you. It seems that there is a lot of future in disciplinary in this aspect.
Yes, and what we can see is that we can see many papers emerging now about this, and not only on surface solar irradiance retrieval, in retrieval from satellite in general. And if you're looking at the standard metrics, then of course it has been trained to be better than the physical approach. So you get better results at a first glance. But when you look at details, then you discover some problems and non-realistic behavior of the statistical learning. So don't trust for the moment. I think it's the recommendation we have. The paper saying that we have the solution with the machine learning approach. Forget about the physical domain. We have the solution. No, it's not. It's still ongoing research.
Thank you. Is there any other question from the audience?
Yeah. Can we take a group photo with Professor?
Yeah, with pleasure. It's a good idea because it's nice to see how many people who are connected during. It's an honor for me for doing this talk. I hope that it was of interest.
Please on your cameras.
You have to say when it's okay. Who is taking the screenshot?
Okay. 1, 2, 3. Oh, thank you.
You're welcome.
Good afternoon, Franco.
If we don't have any other questions, I want to personally and on behalf of EXCELSIOR and ERATOSTHENES team, thank you. for accepting the invitation. And also I'm looking forward for the next trainings and next talks, so we can have more discussions about the cameras, etc.
Yes, with pleasure. Within the project Atari as well, we have plenty of time to exchange, to collaborate, to develop together. And I've also new places where to install instruments as well. It's so important to have in situ measurements. So thank you for giving me and us the opportunity to first exchange some ideas about this.
And also thank everyone for joining us today. I will be sharing the record with you, I guess, in this week. So thank you again and enjoy your day, everyone.
Bye. I will send you the link to the presentation for you to have.
Bye-bye.
Thank you very much. Thank you again.
Bye.
Bye.
Bye.